Yeah, guys, I'm just going to go through a pretty buzzy concept for in calculus, and that is the idea of a composite function. So if you just googled composite functions, you'd come up. There'd be heaps of examples, right? There's actually infinite examples because it's basically, think of what does composite mean? Well, it means it's composed of two things, and you guys now have a good deep understanding of what a function might be. So a composite function is just functions that are composed of one another. They are linked in a certain way. So basically the definition here is the result of one function substituted into another function. So I'm reading it because my handwriting is terrible and it's something I'm working on, but the result of one function substituted into another function. So I'm going to get into notation, but let's just have a look. Consider if we have a function f of x and we define that as sine of x, and we have another function, let's say g of x is x squared. There's two functions. Let's have a look at what happens when we compose the two. So let's have a look at f of, and so this is what's happening when we compose f of g of x. So it's just, instead of f of x, we have f of g of x, and so that would just mean that we replace any input, right? So these are both inputs. Now let's make that input instead x squared. So this would be sine of x squared. And so this is f, and we do a little circle composed of g of x. So f little circle g of x, that means composed. Okay, let's have a look at what it might be if we compose it around the other way. What if we had g composed of f and the variable we're dealing with is x? Well, that would be then g, I think we should actually have used square brackets, g of f of x, and well, that's going to be g, which is x squared, and then instead of squaring x, we're now going to square f of x. So, and f of x is sine x, so that would actually be sine x squared. So, yeah, so I guess that's it. Maybe we'll look at one more example. I know this, for anyone who's not in my class watching this, I know that this is sine squared x, we write it like that, but my students, we haven't quite got to there in trig yet, so we're just going to be doing composite functions of polynomials to begin with. So let's have a look at an example of composite functions. Let's say f of x is let's say 2x squared plus 3, and g of x, let's say, is x plus 1. Then what is f of g of x? So we just take g of x, this thing, and we put it in to f of x, and that's f composed of g evaluated in the variable x. So we're putting that in for all x, well, that's just 2x plus 1 squared plus 3. And if around the other way, g composed of f of x, which is g f of x, right? Then we're just taking all of this and we put it in for this x variable. So it's actually just going to be 2x squared plus 4. because this x becomes this entire thing, so 2x squared plus 3, and we're just adding a 1. So it's really that easy. But what we want to do is we want to derive composite functions. So differentiate a composite function. So I might normally ask you to give me an example of a composite function, but we'll go with h of x. So I'm just using h of x because it's because I'm going to be using f and g in a second. So let's say h of x is 2x plus 5 and cube that. So if I ask you to differentiate that now, you would probably have to go and expand this, right? So you're going to get 8x cubed at the start, and you're going to get 125 at the end, and it's going to be this really big polynomial, right? And it's going to take you a lot of time to expand that. But we have this special rule when differentiating composite functions. So let's have a look. Let's have a look at the rule. Given, okay, I need to write neatly. Given the composite function f of g of x, f composed of g of x, or f of gx, the derived function is given by, and I might prove this when we get back to school, is given by f composed of g prime of x. So that's just whatever function we're given. If it's a composite function, its derivative is equal to g of x multiplied by f prime g of x. So that looks pretty confusing, right? But let's have a look at it in terms of this example. So in here, f for this function here, f of x is when we take anything and we cube it. That's how I like to call that, like our outside function. That's our f function here. Now our g of x is the function that's on the inside, right? It's on the inside of this larger function. So it is 2x plus 5. And so here, h of x is actually f of x composed of g of x. So f composed of gx, because if I take this and I put it into that function there, this is my outputted function. So h is actually a composition of two functions. And so we can actually use this derivative rule here. So the inner function, that is 2x plus 5, while its derivative is 2. And the outer function is x cubed derivative is 3x squared. Okay, so we're going to have to use this rule here. So h prime of x is going to be equal to the inside function's derivative. So the inner function's derivative, which is 2, times the outside function's derivative composed of gx. So we have 3 squared, but our inside function is still in there. So it's 2x plus 5. And so our answer is 6, 2x plus 5 squared. And so I tried to go through all the notation and do that correctly with terms of notation. And now here's my take on it from my personal experience. If it's a polynomial with a power, bring the power down the front, reduce the power, times by the derivative of the inside function. So if I was doing this now, I would just go 3, 2x plus 5 squared. So I just treat this like some variable. So there's nothing in there yet. So then leave it in there, and that times by the derivative of the inside function. So let's have, that might be a good record of learning. Okay, and let's have a look at another example. So let's have a look at this example here. Y equals x cubed minus 4x squared plus 6 all to the 4. So outside function, f of x is x to the 4, isn't it? It's taking anything, raise it to the 4th power. Inside function, g of x is the function on the inside. So x cubed minus 4x squared plus 6. And so if I wanted the derivative of this thing, so y prime of x, then this is going to be, you could always write y as y of x, but remember this is just from that kind of year 11, 12, all your prior algebraic notation was always y, so I'm just going to do one like that. Y prime of x, bring that power down, leave the inside function, reduce the power, and now times by the derivative of the inside. So times by 3x squared minus 8x, and that 6 would be its derivative 0, and we bracket that because we have to times by that whole thing. You could put that 4 into there. We could call this 12x squared minus 32x, all in brackets. That's just this multiplied by that, and then times by x cubed minus 4x squared plus 6, all cubed. And what we call this is chain rule. So chain rule, because these functions are linked together, right? So they're linked together, we call this the chain rule. And so if we were to derive, so f composed of g evaluated at x, if we take the derivative, that would just be f prime with gx still in it. So we did f prime, we did 4, we reduced the power, we put the power down, reduced it, and left the inside function. So that was that bit there. I was just deriving the outside function and leaving the inside function, and then we times by the derivative of the inside function. So it's times by g prime of x. So here it is, that bit there, that's f prime with gx in it, and then this here is multiplied by g prime of x. And that is the chain rule. I'll do one more example. Let's differentiate they're usually h of x if they're a composite function, 1 over x squared plus 4. Alright, well, h of x is obviously a composite function. f composed of g, and a variable is x, naturally. G of x is the inside function, so it's x squared plus 4. And f of x is 1 over anything. So there's your big function, 1 over this thing, and there's your inside function. And later on in calculus, it'll be important to make those choices. But right now, they're going to be all pretty obvious. So h prime of x is going to be f prime with gx in it times g prime with just x in it. And so let's have a look at this. G prime of x is just 2x. And f prime of x, well, remember this is x to negative 1. So to derive it, it's going to be negative x, bring that 1 down, and then reduce the power. So it's going to be negative 1 over x squared. And so h prime of x is f prime, negative 1 over whatever gx is, squared, because that's our input. So that's going to be x squared plus 4 squared. So that's just the derivative of the outside function, then put gx back in, multiplied by g prime of x, which is 2x. So this is going to be negative 2x all over x squared plus 4 to 2. Nice, and there's just one little thing I want to just add. So I realized when I was doing this problem, when I had a y, there's two different notations. Differentiating notations. If it was a y equals some function, then the derivative is dy dx. And that is, I'm going to spell it wrong, Leibniz notation. So Leibniz was a man who invented calculus, supposedly at the same time that Isaac Newton invented calculus. So this here, this is Newton's notation. So Newton invented calculus independent of Leibniz, apparently. Some say that Leibniz stole it from Newton, and some say it was the other way around. But we respect both of their discoveries because they're both very smart men, and we interchange with their notation. So obviously Newton's is quite nice because it's just f prime, and then every derivative after that is just a prime added, or f fourth derivative, and so on and so forth. Whereas Leibniz notation is a little messier because it's basically rise over run, which is change in x over change in y, and that's a delta symbol, so that's delta y over delta x, and that's where the d's come from, dy over dx, delta y over delta x, change in y over change in x. So that's Leibniz notation, and that's Newton's notation. So on that earlier problem, I should probably have gone dy dx when I took the derivative, but alas.